Welcome to Visual Algebra Lecture 4.4, Subgroups of Quotient Groups. In the previous lecture, we proved the first of the four isomorphism theorems, the fundamental homomorphism theorem. It says that every homomorphic image is a quotient. The next natural question to ask is, what can we say about the structure of a quotient? In particular, what are its subgroups? Which ones are normal? What are the conjugacy classes? These questions and more are addressed by the next isomorphism theorem, the correspondence theorem. We'll prove the main part and explore it through a visual analogy that I call shoebox diagrams, which I think is unique to my book and video series. We will also heavily rely on subgroup lattices throughout. Okay, let's get started. The fundamental homomorphism theorem, or FHT for short, is the first of four basic theorems about homomorphisms and their structure. These are commonly called the isomorphism theorems. Some sources number these theorems and others give them names. However, the order in which they are presented varies wildly. I like to joke that it's like the last four gifts on the song 12 Days of Christmas. Every version does it a little bit differently. Because of this, I prefer giving them names. Additionally, I hope to convince you why the order that I'm presenting them in is absolutely the most natural way to do it, especially given our visual pedagogy and using subgroup lattices to illustrate the concepts. The first isomorphism theorem is what we saw in the last lecture, the fundamental homomorphism theorem. And that really does come first, pretty much in all sources, although sometimes it's not considered one of the isomorphism theorems. And this says that all homomorphic images are quotients. And once we know that, think about what the next natural question should be. Well, of course, it's what do we know about the structure of a quotient? In particular, what are its subgroups? And that's what the correspondence theorem, which is the topic of this lecture, will tell us about. It characterizes the subgroups of a quotient and the structure of the subgroups. For example, which ones are normal and which ones are conjugate. And once we know that, and we understand what the normal subgroups of a quotient are, then what should we ask? Naturally, what happens if we take the quotient by one of these normal subgroups? In other words, what is the quotient of a quotient? And that's the third isomorphism theorem that I call the fraction theorem. And finally, our fourth isomorphism theorem, called the diamond theorem, talks about the structure of something called a subquotient. And I'm going to have to just tell you to wait 2 lectures until we get there. It really does build off these last two if we have a subgroup lattice point of view. If we don't, then really any of these last 3 can be proven in any order. They just build off of the fundamental homomorphism theorem, and very often the diamond theorem comes second, and the fraction theorem comes fourth, or some other permutation. But when we understand what these really mean in terms of subgroup lattices, I think you will agree that this is the most natural way to order these theorems. The isomorphism theorems all have analogs for many other algebraic structures like rings, vector spaces, modules, Lie algebras, and more. All of these theorems, if you just look at their algebraic statement, can look messy and unmotivated. However, they all have beautiful visual interpretations, especially involving subgroup lattices, but also involving things like Cayley graphs as well. In the previous lecture, we just saw the fundamental homomorphism theorem. In this lecture, we will study the correspondence theorem. Once again, to motivate the statement, given a normal subgroup n of G, we know the quotient G mod n has a group structure via the following operation. An times Bn is the coset ABN. Moreover, by the fundamental homomorphism theorem, every homomorphic image is a quotient. So the natural question to ask is, what are the subgroups of a quotient? Fortunately, this has a simple answer that is easy to remember, and it's called the correspondence theorem. Informally, the subgroups of the quotient G mod n are quotients of the subgroups H of G that contain n. Moreover, most properties of H mod n, that is a subgroup of G mod n, are inherited from H as a subgroup of G. Now, I just said this is easy to remember, and I gave you a few long, complicated sentences. But bear with me. By the end of this lecture, I think you will agree that the answer is not that complicated. And it is best understood by interpreting the subgroup lattices of G and G mod n. Let's do some examples for intuition, and then we will state and prove the correspondence theorem formally. Our running example for this lecture will be the dicyclic group, Dic6, and the normal subgroup n, which is generated by r cubed, that we will quotient out by. So n consists of 1 and r cubed. It has order 2. And if we take the quotient of G by n, we get the dihedral group right here. Now here are the 6 cosets. And the correspondence theorem is all about how the subgroup structure of the quotient comes from the subgroup structure of the original group. And we know the subgroup structure of this quotient, D3. In particular, there's a subgroup of order 3 consisting of these 3 elements. Each of these elements of order 2 generates an order 2 subgroup, and then there's the trivial subgroup and the entire subgroup. The correspondence theorem says that the subgroups of the quotient G mod n, namely the 6 subgroups that I just said out loud, are precisely the quotients of the 6 subgroups of G that contain n, that is, that contain r cubed. Let's dive in and do an explicit example. So we know one of the subgroups over here. Let's just pick one. How about the one of order 3 generated by the coset Rn? This is Rn and this is R squared n. So that subgroup consists of these 3 out of 6 cosets. And if we think of these cosets as shoeboxes, each one containing 2 shoes, that is the elements, then if we take the lids off these boxes, exposing the elements inside, we see that the elements that are in these 3 cosets are precisely the ones in the subgroup generated by R in the original group. That is right here. So in other words, if we start with this subgroup generated by R, and we take the quotient by n, in other words, this is the quotient of a subgroup by n, that's the same thing as this subgroup of the quotient. In other words, there's a one-to-one correspondence between the quotient of the subgroup and a subgroup of the quotient. Let's do one more example. Let's take the subgroup of the quotient consisting of these 2 cosets. So this one here is, this is just n. This one here is Sn. So that consists of these 2 shoeboxes. And if you take the lids out of these shoeboxes, you get these 4 elements, or you can see inside, and these 4 elements right here, let me shaded like that, are precisely these four elements right here. So if I take this subgroup of G and I take its quotient by n, then that corresponds to this particular subgroup of the quotient. And that's the correspondence theorem, or at least the first part, the main part. Here's that same example, but using subgroup lattices to illustrate the main ideas. I think this just adds extra intuition. On the left, we have the subgroup lattice of the group G, that's the dicyclic group, and this is the subgroup N, the one that we are quotienting out by. The correspondence theorem says that there is a one-to-one correspondence between subgroups of G that contain N, that is these 6 that I've highlighted, and subgroups of the quotient. And the quotient is generated by the cosets Rn and Sn. So this right here is the quotient. And you can see that. This one corresponds to that, these 3 correspond to that, and so forth. But let's look at this middle picture. This middle picture is what we get by taking the subgroups of G individually and taking the quotient of each by n. So this here, this lattice consists of the quotients of the subgroups, whereas over here, this lattice consists of the subgroups of the quotient. And the correspondence theorem says that these are the same. These are just 2 different ways to write the 3 shoeboxes. You can think of these 3, or in this case, yeah, let's do down here because that's what we have down here, the 2 shoeboxes. You can think of this set as the 2 equivalence classes of size 2, that is the boxes with the lids off, or just as the 2 cosets, that is the boxes with the lids on. So here's that same subgroup that we just saw at the end of the last slide. And this one here corresponds to, the 4 elements here are the 4 elements in this subgroup. And if we take the quotient of that by n, now we get 2 equivalence classes, that is 2 cosets. And those 2 equivalence classes, or those 2 cosets, are the size 2 subgroup of the quotient G mod n. The correspondence theorem actually says more than just this. Not only is there a bijection between the subgroups of G that contain n and the subgroups of the quotient, but basically everything that we want about this lattice to be true is true and is inherited from this lattice. Now, what do I mean by that? Well, the index of this subgroup in here is the same as the index of this subgroup in here. The intersection of 2 subgroups over here is corresponds to the intersection of 2 subgroups over here. And I'll formalize this pretty soon. The normal subgroups over here. So let's write these are the normal subgroups that contain n. Those correspond with normal subgroups over here. And these 3 subgroups are conjugate in G. So the corresponding groups in the quotient are conjugate as well. Basically, properties of the lattice in the quotient are inherited from properties of the lattice in G, and vice versa, as we'll see. Not only can we deduce everything about this lattice from this one, but sometimes we don't know enough about this one because it's bigger, but we can inherit properties about this from properties of the smaller lattice that we know well. To summarize, not only is there a bijection between subgroups of the quotient and subgroups of G that contain n, but everything we want to be true about the subgroup lattice of the quotient is inherited from the subgroup lattice of G. Most of these can be summarized sort of like the following. The blank of the quotient is just the quotient of the blank. Let's now state this formally, and while most of this is a bit heavy symbolically, I'll do some examples right away to explain what these parts really mean. And they're not as hard as they look. So let's suppose that we have a normal subgroup N of G, and we have two intermediate subgroups H and K. Then subgroups of the quotient G mod N are quotients of subgroups H that contain N. We've already stated that multiple times. But moreover, H mod N is normal in G mod N if and only if H is normal in G. The index of H mod N in G mod N is the index of H in G. The intersection of two subgroups in the quotient is just the quotient of the intersection of the two subgroups in G. That's an example of a statement like this. The blank of the quotient is the quotient of the blank. The subgroup generated by two things in the quotient, H mod N and K mod N, is the quotient of the subgroup that H and K generate in G. And also, finally, H mod N is conjugate to K mod N in the quotient if and only if H is conjugate to K and G. Now, this is a more general case of the second statement, but I think it's helpful to see them separately. Now, we could extend this list if we wanted to, and some sources do. We could talk about the correspondence between subsets of a quotient and subsets of G that contain N. We could talk about normalizers in the quotient versus normalizers in G. So the normalizer in a quotient is the quotient of the corresponding normalizer. But I think this list of 6 really covers the most important points. And I'll let you explore anything else you want as an exercise. All parts of the correspondence theorem have nice subgroup lattice interpretations. We've already interpreted the first part. Here's what the next 4 parts say. So the second part said that H mod N is normal in G mod N if and only if H is normal in G. In other words, if the conjugacy class of H mod N has size 1, then the conjugacy class of H has size 1. The third part said that the index of H mod N in G mod N equals the index of H in G. So that means that if we label the subgroup lattice with, say, A, the index, then those labels are preserved, not only here, but everywhere else. The fourth part says that the intersection of two subgroups, say H mod N and K mod N, in the quotient equals the quotient of the intersection by N. In terms of the subgroup lattice, that means if you have two subgroups, H mod N and K mod N, and you take their intersection, well, you get the largest subgroup that is contained in both. Well, another way to get that is to take H and K in the original group, intersect them, the largest subgroup that contains both, and then mod out by N. Take the quotient by N, and you get the same thing. The fact that these two things are equal, well, the one on the right, you can think of this as the intersection of two collections of shoeboxes, and the one in the middle here, or on the left, is a subgroup of G mod out by N, so that's like shoeboxes with the lids open. The fifth one is analogous, but it's for what's above these two subgroups. So the union of two subgroups is not a subgroup, but given H mod N and K mod N, we can say what is the smallest group that contains both. and that is the intersection. Sorry, that's the subgroup generated by these two things. And that's the same thing as starting with H and K and taking the subgroup that they generate and then taking the quotient of that by n. So the fourth part is down here, or equivalently here, and the fifth part is that these two sets are equal right there. And that completes the next four parts of the correspondence theorem. 2, 3, 4, and 5. The last part of the correspondence theorem says that we can characterize the conjugacy classes of subgroups in the quotient from those of G. So two subgroups in the quotient are conjugate if and only if the corresponding subgroups in G are conjugate. And the earlier parts of the correspondence theorem generally told us things about the quotient from the subgroup structure of the big group G. But in this case, and it's true in the others, but it's especially true here, we can often deduce properties of the subgroup lattice of the big group from properties of the smaller one. Now I want to apply this to an explicit example and find the conjugacy classes of the group C4 semi-direct product C4 by inspection alone. First, I want to remind you of something that I proved in an earlier lecture that you may have missed, and that is if H is a subgroup of order 2, then H is normal if and only if H is contained in the center of G. So down here we have 3 subgroups of order 2, and all of them are what I call unicorns. Also something that I introduced in that same lecture. These are just subgroups that are in a unique lattice neighborhood. So this guy's got 5 parents, this guy's got 1, this one has 3. So any conjugate of these subgroups has to preserve the number of subgroups that they're sitting in. So every conjugate of these have to be themselves. So these things have to be normal. So these subgroups are central, and therefore V4 is central as well. And in fact, this actually is the center. Something that we're going to show at the end of this lecture, we're not quite ready yet. We could do it, but it's a little out of place, is that G mod the center of G cannot be a non-trivial cyclic group. So if G mod the center, or if the center were one of these 3 groups, then G mod the center would be Z2, and that's not allowed. And we know this group is not abelian, so the center cannot be this. So the center has to be V4. That's a little bit besides the point, but I wanted to actually just mention that in this case we can spot the center. So these 3 subgroups are normal, and you should recognize the subgroup lattices that are above them. So let's start with this one. This is that little kite shape is the quaternion group. This one over here, so let me actually write that. So this is Q8. This one, well, let me call this one N1, and let me call this N2, and let me call this N3. So G mod N2 is isomorphic to Q8. G mod N3 is isomorphic to C4 cross C2. I'm running out of room a little bit. That's this lattice. And then here, you may not recognize this exactly, but this is the lattice of D4. So G mod N1 is isomorphic to D4. And there's only 5 groups of order 8, and only one of them has 5 subgroups of order 2. And so, if we were to swap the position of these things and like unfold this, you would recognize how we normally lay out D4. But so these 3 quotients are different, and we know the conjugacy classes of these. We don't necessarily know them of the full group because we haven't seen this lattice before, but we know the conjugacy classes of these quotients. Starting with the quaternion group, we know all of these subgroups are normal. That's something that we've seen before. Well, this group over here is abelian, So all of its subgroups are normal. And finally, for D4, we've seen that the order 2 subgroups come in size 2 conjugacy classes, then except for the center, and then everything else is normal. So these are the conjugacy classes, and what the correspondence theorem says is that these things pull back to the conjugacy classes of the big group. In other words, for this entire group G, we know that these two subgroups have to be conjugate, as do these two, and everything else, or at least all of these things, have to be normal. Now, we can't necessarily say, from this we can't, well, actually, yeah, from here we can say that, so all of these, so let's see, so I have to circle this one as well. So we can say that all of these subgroups, I'm doing some of them more than once, have to be normal. And of course, the trivial group is normal as well. So we've just determined the conjugacy classes of all of the subgroups of G just by using the correspondence theorem and what we know about the conjugacy classes of these three groups of order 8. And I think that's pretty cool. That's powerful. At this point, hopefully I have fully motivated the correspondence theorem and explained not just what it says and what it means, but why it says that. I think the shoebox diagrams do a good job of that. I want to actually prove the statement. I'll just do the first part, but that's the main part, the actual correspondence between subgroups of the quotient and quotients of subgroups that contain n. The rest of it is mostly just exercises in notation, and so I will leave them as exercises. I might say a few words about them. So for the proof, we have to understand what subgroups of the quotient are. So let's let S be a subgroup of G mod n. So what can we say about S? Well, S is a collection of cosets. And S is some set of cosets of the form Hn, where H is in some set. This is a subset of G, and we have to show that this is actually a subgroup. So let me write that down. So claim H is a subgroup of G. So again, the elements of G mod n are cosets, so we have some collection of them, and we're going to let H be the set of all representatives. I claim that H is a subgroup. And we'll use the one-step subgroup test. Let me write that down. One-step test. So we will take H1 and H2 in H. Well, then H1n and H2n are in S. And so H1n times H2n inverse also is in S. Let's write that as H1n times H2 inverse n, or H1 H2 inverse n, which is in S. But look at this. Big H is the set of all things that are representatives of cosets in S. And so this tells us that H1 H2 inverse is in H. And that's exactly what we had to show with the one-step subgroup test. So that's one direction. In other words, it shows that if you have a subgroup of the quotient, it is a quotient of the subgroup, but the correspondence means that there's this bijective correspondence between the two, so we have to show that every subgroup H that contains n has to define a subgroup of the quotient. So in other words, conversely, suppose we have a subgroup H that contains n. We want to show that H mod n is an actual subgroup of G mod n. And we know this is a set of cosets. So how do we do that? Well, we've basically done it up here with the one-step subgroup test. So let's take, I'll write it again, H1n and H2n in H mod n. Then H1n times H2n inverse. I'll just write this as H1, H2 inverse n. Well, that is by definition in H mod n, because this thing here is in H. And that's what we had to show. So that's the correspondence theorem, or that's the first part. Now, the other parts, 6, I'm going to leave as exercises. And I encourage you to try them. Let me say a bit about one of them. So one of the parts, I forget which one, says that H mod n is normal in G mod n, if and only if H is normal in G. And I just want to show you why these really aren't that bad. So what does it mean for H mod n to be normal in G mod n? Well, that means that if you take any element in H mod n, so let's say Hn, and you conjugate it by something in G mod n, so Gn times Gn inverse, which, by the way, is Gh G inverse n, then you remain back in Hn. In other words, this is equal to some element of the form, say, H1n in H mod n. But now, what does it mean? Well, what does this mean? This is true if and only if every time we conjugate an element in H, we end up back in H. So this is true if and only if GH G inverse equals H1, in other words, is an H for all G in G and H in H. And that's what it means for H to be normal in G. So I'll let you write this up formally. It's good practice to not just write down and see why it's true, but also write down a nice coherent proof. And the other parts, like the intersections and the indices, the index of subgroups in larger groups, those are all very similar. Just exercises in notation and formal mathematical writing. Last but not least, I want to revisit an exercise that I promised I would come back to when we were exploring the subgroup lattice and conjugacy classes of the semidirect product of C4 with C4. And namely, that is, if G mod the center of a group is cyclic, then G is abelian. Now, if you think about this for a few moments, you realize that something actually stronger is true. If G is abelian, then the center is equal to G. So G mod the center isn't only cyclic, it's trivial. So we can actually add this and say, and thus G mod the center is G mod G, which is just the trivial group. So as a corollary, G mod the center can never be a non-trivial cyclic subgroup. You may say, well, why not just state that? Well, the proof basically, it's fairly straightforward to show if this, then this, and then we get the stronger thing for free, rather than prove the stronger thing directly, which I don't know how to do. I haven't really thought about it. So this is something that follows from the correspondence theorem, and I think it's nicely visualized with our shoebox analogy. And so let's see how it goes. So G mod the center. assuming it's cyclic, that means it is generated by a single element or a single coset, little gz, where z is short for z of g. So if the center down here consists of a bunch of elements, let's say the identity and then z1, z2, z3, etc., it might be finite, it might be infinite. That means that the cosets, so all the other cosets are gz, g squared z, all the way up to g to the n minus 1z. And this also might be infinite. I don't have to imply that this is finite. But all the cosets are some power of g times z. Well, that means that every element is of the form g to the I, for some power of g, times some element in the center. So in other words, G is the set of elements of the form g to the I times z, where I is some integer and z is in the center of G. So why is this abelian? Well, let's take two elements. Say A and B are in G. Say that A is equal to g to the I z1 and B is equal to g to the j z2. Then A times B is, well, the z's commute with the powers of g, so all of these things commute. So A times B is g to the I z1 times g to the j z2, and I can rearrange this however I want to, so I can certainly, g to the I plus j z2 z1, for example, or I can write this as g to the j z2 times g to the I z1, and this is equal to b times a. So indeed, if G mod the center is cyclic, that means every element looks like this, any two of these things will commute with each other. What this means for subgroup lattices is that the center can never be too high up in the lattice. So here's C7 semi-direct product C6, which is order 42. And the other subgroups have order 21, 14, and 7. And these have to be normal because they are the unique subgroups of their order. So we know that we can take the quotient of G by them. And the quotient of G by this one has order 2, so that's C2. This by this is going to have order 3, 42 over 20 over 14. So this is C3. And then G by C7, this is going to have order 6. And the subgroup lattice, we can recognize it as C6. So the center cannot be any of these three subgroups because that would lead to a cyclic quotient that is not trivial. That's impossible. And we know the center is not G itself because this is a non-abelian group. So let's see what we can say about the subgroup lattices. So these are all normal. These subgroups of order 2 are all conjugate. None of them are normal. I guess technically we don't know how to prove this, but it seems reasonable that we're not going to have a conjugacy class of size 3 and another one of size 3 and one of size 1, but I guess we could. We will shortly, by next chapter, learn how to prove that all of these things have to be conjugate. And by the single parent property, because these are conjugate and they each have one parent, these things have to be conjugate as well. Single parent property is also something I talked about in chapter 3. And also by the single parent property, since these are conjugate and they each have one order 3 child, these have to be conjugate as well. So in other words, the only normal subgroups here are the ones that I'm highlighting in yellow. And I've already eliminated these 4 from being the center. So the center of this has to be C1 because the center is normal. So that's a fun little exercise. And there's a lot of examples that where you can take subgroup lattices and deduce properties of the conjugacy classes, the center, not always the center, but normalizers and things like that, just from the lattice and from what we know about the isomorphism theorems. I like to put a lot of problems like this on exams. I like it because they are original problems. And these are things that, you really can't do this without our visual repertoire. It's not an instead of, it's just a different skill set. So you could maybe figure this stuff out. It would take a long time. You certainly cannot do it just in a couple minutes by inspection. So that's a skill set that I think is in addition, not instead of, what you learn in a regular group theory course. And it adds a lot more insight and knowledge, holistically into the structure of groups. So this lecture, again, was all about the subgroup structure of a quotient. And what's coming up next, now that we know what subgroups in a quotient are normal, we can quotient out by those and say, what happens when we take the quotient of a quotient? So that's coming up next. That's called the fraction theorem. That's my name. It's often called the freshman theorem or the third isomorphism theorem, or I think it's got a few other names that I don't remember. But I think the fraction theorem I think you'll grow to like that one best. And there's also a lot of neat visuals in there that you will never see. You probably won't see anywhere else. So make sure that you stick around, and I'll see you then.